Welcome back to another video on my channel, math_exe. Today we're going to look at the sequel of arithmetic sequences, geometric sequences. So a geometric sequence is a sequence that has a pattern of multiplying or dividing a constant, and that constant is usually called the ratio, symbolized by the variable r. So basically, for example, you have a term, you multiply by the ratio to get the next term, and then multiply by the ratio to get the next term, and then you can just do that all over again. Okay, so the formula for the nth term of a geometric sequence is as follows. So we have t of n is equal to a times r to the n minus 1, where tn is the nth term, a is the first term or t1, and r is the ratio. So some examples of a geometric sequence is in the form of something like this. So we have t1, and this is to get t2 you multiply t1 by r. To get t3 you multiply by r by t2, something like that. And it also looks probably something like this. So we have 1, 2, 4, 8, and notice you multiply 2 to get the next term. So 2 is equal to 1 times 2, 4 is equal to 2 times 2, and you can do this so on. And there is a simple visual proof, just like the arithmetic sequence one. So we can just rewrite the terms and be faced with this. So we have a as the first term, and then we have a times r, because the pattern here is we multiply by r to get the next term. And here I should have mentioned that r is the ratio. And then for t3 it's r squared, because you multiply by another r, so it's basically becoming a times r times another r, and then you can just combine them together to get a times r squared. And then same thing for t4. And I can just rewrite the exponents of r slightly different, like so. So notice we have a times r to the 1 minus 1. Notice 1 minus 1 is just 0, and r to 0 is just 1, so it doesn't change anything. And we can just do the same thing as all of these. And notice these exponents correspond to the term order. So this one corresponds with 1, this 2 corresponds with 2, this 3 corresponds with 3, and then so on. So if you're asking for the nth term, let's say tn, that means this n must correspond to the exponent of r. So just write this ar to the whatever n is minus 1. So this is where the formula originates from. So next, the formula for the sum of the first nth terms in a geometric series is as follows. So we have s of n is equal to a times in brackets 1 minus r to the n, and this is over 1 minus r. And keep in mind that r cannot be equal to 1, because if we plug in r equals 1, it will be an indeterminate form. In this case, Sn is the sum of the first n terms in a geometric sequence, r is the ratio, and a is the first term or t1. Now, what I like with this formula is the proof. The proof is pretty interesting. So suppose the sum of the first n terms of a geometric sequence is as follows. So we have a as the first term, r as the ratio. So the second term will be a times r, just like we've seen before. And then we stop at the nth term, which is just ar to the n minus 1. And then we can just make a copy of this sequence, except we might want to multiply this by r. So if r times s of n, and notice I rewrite this sequence slightly different. So notice we have I select the what's supposed to be ar right here, since we're multiplying by r. slightly towards here, and then we do the same thing right here, and then what is supposed to be AR to the n minus 1, when we multiply it by r, we get a times r to the n. And the reason I will do this kind of like sliding stuff is because I want to subtract them, and notice this whole thing, box in red, will cancel out. So we're only left with s minus r times Sn is equal to a, and then minus a to the Rn. Factoring out the Sn and a, and then finally dividing by 1 minus r to get the original formula right here. And one thing I also like about geometric series is there's a formula for a infinite geometric series. However, it is conditional, as you see here. So the formula for the infinite geometric series is s of infinity is a over 1 minus r. And this only works, it converges. Converges means it approaches to a finite value. So meaning it means that it's a fixed value, it's not infinite. And this only applies if the absolute value of r is less than 1. So what I mean by the absolute value, so if we assume we have a negative value of r, let's say negative a half, we don't consider the negative sign, we just delete this, and then we only take the positive version of this, which is just a half. If we also have a positive value of r, let's say a third, then it's just the same, since 1/3 is already positive. And you might be wondering what will happen if r does not satisfy this criteria. So what that means is, what if r is, the absolute value of r cannot be less than 1, it means it can be greater than 1, or possibly less than -1. So what that means is the geometric series will increase. So assume the ratio in this case is 2, which doesn't satisfy this criteria. So we're just multiplying by 2 on and on and on. And notice the terms are increasing. It means it will the infinite term will be possibly infinity, and therefore if we just sum those up, it will diverge to infinity. Diverge means it will approach to an infinite value, either positive infinity or negative infinity. And like the sum of the first n terms of a geometric sequence, we can also do something similar to this proof. So let the sum of the infinite geometric series be like a plus a r plus a r squared, and this goes on and on into infinity. And what we can do is just duplicate this s of infinity, except we're going to multiply this by r, and then we can just do the slide thing. And keep in mind, I've assumed that the absolute value of r is less than 1. So notice if we subtract this, notice all things boxed in red will cancel out. So we can just, we're left with s of infinity minus r times s of infinity equals a. A is the only term left. Factoring out a s of okay, so we're going to look at some special properties of like geometric sequences, the sum of a finite and infinite geometric sequence. So let's look at the first one. Define r as the ratio in a geometric sequence and t of n as the nth term of a sequence. Then it follows that r is equal to the m minus nth root of tm over tn. And keep in mind that m and n are natural numbers, and m must be greater than n, and n must be equal to or greater than 1. So this can be easily proven by extending the definition of T of n. So next and final one, define S of n as the sum of the first n terms in a geometric sequence, and T of n as the nth term of a sequence. Then it follows that T of n is equal to S of n over S of n minus 1. And this works for all natural n. So that's it for the special properties and everything about geometric sequences. Let's move on into some examples. Alright, for the first example, given a sequence 1, 3, 9, 27 and so on, the terms go on towards infinity. Given the 2021st term is 3 to the a, and we need to find a. And next, we're going to find the sum of the first 6 terms, and then show that the sum of all terms will diverge or it will approach infinity. Alright, so we can just determine the ratio by just simply notice that we can we multiply by 3 to get the next term, and therefore our ratio must be 3. And since we know the ratio and the first term, which is just 1, we can use our general formula for a geometric series. So T of n is equal to a r to the n minus 1, or 1 times 3 to the n minus 1, or it would be just 3 to the n minus 1. Alright, substituting 2021 to find a. So T to 2021 is equal to 3 to the a is equal to 3 to the n minus 1. And since exponents are increasing functions, we can just eliminate the 3's out and just focus at the exponents. So we're just left with a equals n minus 1. I should have just substituted 2021 right here. So a is equal to 2021 minus 1, which is just 2020. There we go. That's the answer for part A. Part B, we need to find the sum of the first 6 terms. And we can just simply do that for our formula. S of n is equal to a times 1 minus r to the n over 1 minus r. And the sum of the first 6 terms, we can just substitute n equals 6, and we know r equals 3 and a equals 1. So a equals 1, so 1 times 1 minus 3 to the 6 over 1 minus 3. So on top we get 1 minus 3 to the power 6. We can just visualize this as 3 multiplied by 3 multiplied by 3 6 times. And perhaps we can just group some terms right here to make everything simple. So we have 9 times 9 times 9. 9 times 9 is 81, and then multiplied by 9 we'll get 729. So there we go. And the bottom will be negative 2. And this will be negative 728 over negative 2. The negatives cancel. It will leave us with an answer of 364. Yep, that's the answer. And then for the last one, it's pretty easy to see. So remember the criteria of a sum of infinite series. So we have a minus 1 minus r if the absolute value of the ratio is less than 1. Here in this case, our r is 3. The absolute value of 3 is just 3. 3 is less than 1, which is a contradiction, and therefore the sum of the infinite geometric sequence in this case will diverge. Alright, so that's it for the first example. Question number 3 is a word problem. Given the initial population of a country in year 1 is 200, the population of the country doubles for every year. So from this, we can just visualize the year n as the nth term if we look at this as a geometric series. So we can just write the series as first year 1, or I would say term 1, T1 I guess. And then the population doubles for every year. That means we multiply by 2 to get the next term or the next year. Meaning we can just see that the ratio will be equal to 2. And then we know the first term is 200. I'll just write the sequence anyways. Probably until the third term and then so on. Alright, from this information we can just simply calculate the population of the country in year 8. That means, but first we need to just write the general form of this. So Tn is equal to Ra times R to the n minus 1, which is equal to 200 multiplied by R is 2, and it's something, so something like this. And we know we want to find T of 8, the population in year 8. So it will be 200 times 2 to the 8 minus 1. It will be 200 multiplied by 2 to the 7. Now 2 to the 7 is just multiplying by 2 7 times. So something like this. Probably group some terms right here. 2 times 2 times 2 is 8, 8 and 2. Meaning this will be 8 times 8 is 64, times 2 will be 128. So it will be 200 times 128. This will leave us with 25600. There we go. So that's the total population of the country in year 8. And the population is escalating very quickly too. So anyways, for part B, find the increase in population. It's just pretty easy. You can just subtract T8 by T1. So T8 minus T1 is equal to 756 to 25,600 minus the initial population is 200, and it's just 25,400. And that is a pretty large increase of population. Anyways, let's jump into the last example of this video. Or for the last example, the first and third terms of a geometric sequence are 243 and 27 respectively. So we know T1 is 243 and T3 is 27. We can just write the sequence kinda. So let's see what we have. So we have 243, and then the second term we don't really know yet, so let's just leave a blank right here. And then we know the third term. So what is part A asking? We need to find the ratio. And typically it's pretty easy, because notice we multiply by let's just call the ratio R to get the next term, and then we multiply by this again to get the next term. We can just make an equation out of this. So notice we get 27 by multiplying 243 by R and R times R. So something like that, which simplifies to 243 R squared. And typically we can solve for R squared at this point by just first dividing both sides by 243. The left hand side will simplify to 1 over 9. So you can just do that on your own. You can just test the division and stuff. And next we can just I'll just write 1 over 9 equals r squared, and therefore we can just square this up. So there we go. And since we're taking square roots, we might as well put a plus or minus right there, so leaving us with two possible values for the ratio. R is positive 1 over 3, or R equals negative 1 over 3. And I should have mentioned find the possible values of the ratio, and therefore for part B we might as well do using our two possible ratios, we might as well solve for all possible values of the infinite geometric series. So might as well separate this into two cases. So when r equals 1/3, this will become the infinite series is a over 1 minus r. Remember, our first term is 243, and this will become 1 minus 1 over 3. There we go. And the bottom part will be 2 over 3. We can just visualize this as a division problem. So 243 divided by this number, which will leave us with 243 times 3 over 2. And then calculating this, we'll get this will be equal to 729 over 2. Or you can just simplify this into a mixed fraction if you want to. So this is when r is equal to 1/3. On the other hand, when r is equal to negative 1/3, the series will become something like this. So the infinite series is again, and you can suppose, you can just claim the check that the absolute value of r is less than 1. However, I'm not going to do that. You can just do it on your own. It's pretty obvious. So remember, the first term is 243. The bottom part will become like so. 243 over, the bottom part will be 4 over 3. Rewriting this as a division problem, flipping the numerator and denominator, we'll get the answer will be 729 over 4. So our friends' final answers are, the infinite series could be either 729 over 2 or 729 over 4, depending on which r value you are taking on. And usually when there are like several different values of r, usually it just says that if r is positive, find the ratio of the geometric series or something like that. However, I just including both cases because I thought it would be pretty interesting. So anyways, thank you guys for watching this video. Please subscribe for more videos, and I'll see you guys in the next video. Goodbye. And before you go, I just want to mention that I forgot to show you some questions. So here it is. You can just do this on your own, and I'll just give you some time before I end this video. Also, thank you guys for watching this.